אבל כאילו ביקשתי למצוא זה כן ישראל.
זה לא בדיוק מה רוצה. אתה מסכים?
תראה מה נגיד לא מגיע.
לא, אז אני לא נותן, נראה לי איזה שבוע. אולי מנספול וזה. כן. לא משנה, אני חושב שזה בסדר, אני חושב שזה טוב שהוא די... אני כאילו, אני לא אכסה אם אני לא אצא. אם אני לא אצא, אני לא אתבאס עליו. כאילו זה קומה רביעית מעלית.
Good morning. Today we start the last chapter. You notice that we skipped 2 chapters from the book, which means that since the exam there will be no problems from these 2 chapters. It's for your pleasure and extracurricular activity. But I have not finished with what I promised. Stock market and bacterial, what is called phenotype switching, is the same theory applied to biology and to market. We'll do it on tutorial tomorrow. And I'll also will ask to record this session, so it will be part of the video. But today we start.
Will be here
tutorial will be in the usual place, so they now learn how to record. At least they promise. Okay. Fundamental limits of uncertainty, namely, we ask if there is something in the laws of this world that prevents us from completely eliminating uncertainty or diminishing it below certain limits. Okay? So far, we only quantified uncertainty, assuming that we don't know this, how much we don't know. We don't know that, how much we don't know. And uncertainty in principle could be arbitrarily small, or entropy could be close to zero as much as we care. But apparently, if there are some fundamental restrictions, then probably it means something about how much we could know about the world. Okay? And what are the physical fundamentals? That definitely some biological, psychological, and other restriction that could follow from physics or that could not follow, but at least in physics we definitely know that there are 2 fundamental restrictions. And what are they?
Uncertainty principle, quantum?
Uncertainty principle, which will now go, it's already called uncertainty. Because there is something in quantum mechanics which essentially quantum means that something is quantized. It tells us that our world is not continuous, it's quantized, and it somehow, and this will be a subject of today's lecture mostly, that there will be some uncertainty related to it. What other physical restriction from other physical theory?
Pauli?
Huh?
Pauli?
Pauli principle is a part of quantum mechanics. Okay, but there is something not quantum mechanical restriction. Second law of thermodynamics is what we spent all this semester discussing. It's just a quantification of how much we don't know and what it means for our measurements, perception, whatever. But there is some very basic physical discipline, mechanics actually, yeah, which tells us about other fundamental restriction. This science called
chaos theory.
Huh?
Chaos theory or not?
Course.
Chaos.
No. Chaos theory is just first of all, chaos theory is this incidentally is the 4th chapter of the book, which we skipped. Anyway.
Energy conservation.
Energy conservation is just a particular, it's not a theory, it's a certain statement that if a system is time translational, then it conserves some quantity which is called energy. If it's space translational, it's conserved momentum. If it's not conserved. What are restrictions? You cannot go...
Relativity, speed of light.
Relativity. You cannot go faster than light. So these last 3 lectures will be about quantum mechanics first, relativity second, and the most interesting part, how they come together. So if you now take these two restrictions, one that the world is quantized, and another that you cannot move faster than light, any physical object cannot move faster than light, imposes some fundamental restriction on the type of information that you can handle. And that's why I included it, even though you can say, well, it's physics, we are not physicists, or we are. It's because it tells us fundamental things about information, in particularly both in mathematical structure and in a way of interpreting. For relativity, it's kind of clear. If it tells you that something cannot move faster than light, that we definitely cannot know anything about regions which are far away and not very far away in the future, so that signal would not come to us. So it's kind of clear. What is much more non-trivial is that relativity tells us that there are some regions in space from which nothing can escape. And this is now related to the third thing, which is called gravity. So relativity by itself is just a statement about mechanics, just kinematics, essentially statement. You cannot move faster. And then you say, yeah, but there is also gravity. Gravity is such a thing that if you have an object, if you want to escape from it and go somewhere, you need to have your kinetic energy larger than your potential energy here. If this kinetic energy requires you to have a speed faster than light, you cannot escape. And that now fundamental importance for information theory, because it tells me that there are some regions in space on which in principle nothing could come out. And then a third element added to it, namely quantum mechanics, tell you the most fundamental statement of quantum mechanics, which will be the subject of today's lecture, is that nothing is local. That's what I really want you to absorb from today's lecture, that you cannot really separate regions of space. And it tells you that whatever you call black hole is not actually separate. It's actually connected. Okay, and that leads to very important consequences, in particularly what probably the most fundamental law of information theory, which in the first time in physics or in science unites all three fundamental constants of physics. Physics has only three fundamental constants. All the other are material constants. For this material is one constant, for that material is another. There are fundamental constants, which is gravity, speed of light, and h bar. So they come together and they define what is the maximal amount of information that a given region of space can have, just of this size. That will be the last lecture. Okay, so it's more or less roadmap for the next 3 lectures. Okay, good. Quantum mechanics. Today we start quantum mechanics. It's essentially trivial, mathematically it's trivial discipline because it's linear algebra. And linear algebra is a mathematical discipline which deals with vectors and linear operators on it. So what quantum mechanics essentially tells us that, again, it's, well, I do it in a deductive way. I don't tell you how we derive all this, how many things we measured and that we did not measure. Just, I hope, it's not a course of quantum mechanics, okay? So I assume that you somehow learned somewhere quantum mechanics or heard about it. But I'll try to be really using very few statements about quantum mechanics which give a huge shadow on information theory, okay? So there are vectors. Any state of a system is defined by a vector. We already did this in the usual information theory when our vectors were vectors like probability vectors, pi, and this is just a set of positive numbers, the sum of which is 0, if you sum over all I. What quantum mechanics does, and we will be using mostly Dirac notations, this would be a vector, okay? And I could run through different series. Sometimes we also use a usual statement, this is just a psi and it has an R. The only difference is that quantum mechanics tells you that any state of a system is characterized by a complex vector, not a real one, okay? So, okay, where's the probability comes? Probability cannot be complex. Well, they will be squared modulus of the component, but for now it's just a vector. And what we need for algebra, we need a vector to define inner scalar product between different vectors. So we can define a dual vector like this, and we can define a product. So if we would have just a real vector, that would be just scalar product of components. But for complex vector, what we really would do, so if we have, for example, one vector which is the sum of vi I, and we have some phi vector which is the sum of ui's, uj's, j's, then the inner product of phi and psi is just a sum over ui, uj's, complex conjugated vi. That's a definition. Okay? Why we need this definition? Because now from these vectors we really need to say what it's here about real world, what it predicts. And the answer is that it predicts measurements, and measurements are determined by different observables. I would usually call it O because it's observable. And it will be a matrix. It's a linear algebra, yeah? So you have a vector, and you also can define matrices, which is a table made out of vectors, not necessarily square. And then you say that what is every such matrix is a physical observable from which you can make a measurement. And what your quantum mechanics predict you about this measurement is the inner product. So if you, for example, interesting, what is the value of this? For example, it could be energy, or momentum, or coordinate, or speed, okay? Or something very, very complicated. You're interested what is its value in some state, let's say psi. So what you need to do, you need to take an inner product like this. This would be now a real number by definition, because you see, this would be this component squared, because there is psi over here, and there is psi over here. So this is just a measurable. That's it. I told you all quantum mechanics. The rest are consequences. Okay? And so now you may ask, what is so strange about it? So we had real vectors, now we have complex vectors. Well, the first thing, which is that this vector is not a vector of probability. This is the probability to observe a given observable. But what is really now non-trivial is that the system can stay in a superposition of different eigenvectors. For example, you can say, let me take O to be an energy, and then I can define eigenvectors I. Each one has its own eigenvalue, energy EI. In the classical physics, you say that the system has an energy. You cannot have different energy at the same time. Quantum mechanically, you say, if I am in a superposition, then generally I can say that my psi is a sum over a i's of different state with I, and this each I has this one. So now if you take this and plug it here, you find out that every energy EI appears with the probability AI squared, and if they are non-zero for more than one I, then you have an uncertainty which is related to the fact that you are in a superposition. Superposition is it's a mathematically trivial statement in a linear algebra, and physically it's totally bizarre. And it's a very unique property of quantum mechanics that you can stay in a superposition of two things. And of course, this is now a source of uncertainty, because I am in a given quantum state. This state is superposition, but my measurements would come out with a different probability. So one time I will see one value of energy, another time I will see another value of energy. I cannot predict the value of energy. I can only predict the probabilities of, like in a in a classical world, the probability. The measurement by itself, we did not define yet, and it's a very bizarre procedure for which I'll talk later, and I want to stay on the mathematical side. But for now, I remark that maybe the most fundamental reasons that quantum mechanics is such a bizarre science, and because it's really not closed. There is a quantum linear algebra, and then say, but there is something which is outside of quantum world, because measurement takes us outside of quantum world. How it does it? If you take this superposition, you measure it, you find out this energy, and then you measure it again, you again find out this energy. And then you measure it again, you again find out this energy. No uncertainty. Right? But in the quantum state, so you can prepare this quantum state again, you can measure, and you find some other energy. And then again, any measurement would repeat it. Which we would say, we would call it collapse wave function and make other different tap dancing around it. At the very end, if I'll have time, I'll give you my own interpretation of it. But for now, as the people in quantum mechanics say, shut up and calculate. So let's do things, let's just not interrupt it. So the first source of uncertainty is a superposition. Superposition, just the possibility of superposition is a fundamental source of uncertainty. But there is another source of uncertainty, which is, you already have on the blackboard, and you also know it, incidentally, because this was the way you learn quantum mechanics.
Interference?
Well, uncertainty principle is what? It's about superposition. You know, Heisenberg uncertainty, there are movies about it, operas. What it's all about? Is it about superposition or it's about something else?
You can't
Conjugate
go
variable.
smaller than
Huh?
you can't go smaller than h bar when you measure two things.
Two things, okay? So now there is other things which is really important, and it's not about superposition. We can take eigenstate, system in an eigenstate, namely energy has a definite value. Or we can system in an eigenstate of momentum, it has an absolutely definite value of momentum. Or coordinate. Let's say still there is an uncertainty. About what?
You cannot know both of them.
Both of what?
Conjugate variables.
Conjugate. It tells you the following things, that look, just for the very simple trivial fact that your observables are matrices, then measuring, for example, you have one observable which is X and another observable which is Z. So if you take the product of these matrices and plug it here, it would give you an expectation value of the measurement in which you first acted by Z. Let's just do it, okay? Psi, psi. This is an expectation value of making measurement Z first, then measurement X after Z, and this gives you an expectation value of this. You can also do it differently. You can do it Z times X. Psi, psi. They are generally not equal because matrices generally do not commute. In 1975, I just entered university. I was 17, and it was 50 years of quantum mechanics. And we were fortunate to have a guy around, Yuri Rumer, who was in Göttingen at 26. And he was already old man, and he gave us, it was course in quantum mechanics in a sense like nostalgic. And so he said, well, Heisenberg returned from this island where he went because he has problem with spring, and then he came back and he showed everyone the tables very excitedly because he was genius, but he was totally ignorant. He never seen matrix, and so he said, I mean, look, I mean, this if you do it like this, it's totally different if you do it like that. And so and of course he was talking about very specific things about spectroscopic data, but this is kind of when they realize it. You start doing with vectors, then there are some things which are that means, what it means that measuring this first or measuring this first give you different results. It means that these two quantities cannot simultaneously have the definite values. Right? If you find this quantity, then this quantity, or with some accuracy, this quantity. So now let's derive this simple statement. It's the statement that says that if you take now this minus this is called commutator, xz minus zx, x a commutator. So if it's non-zero, you can say that take it squared. Right? So we want to bound it. So of course it will be 4 times psi xz modulus psi squared minus psi xz plus zx psi. Okay, so you can write this, which is minus. And of course this is squared and this is squared too. But now you can say that I want to bound it. So if I bound it, I can just erase this. So it's bounded by 4 psi 4. This is 4, and this is psi x z x z psi square. And then there is this Cauchy-Schwarz-Bunyakovsky inequality, which we'll have used several times, which is essentially a squared plus b squared is always larger than 2ab. It says that you can also bound it by psi x squared psi times psi z squared psi. And also there's a factor 4. But this is variance of x, and this is variance of z. So it tells you if this guy is non-zero, it bounds from below the product of variance. So that when this variance decreases, this variance must increase because there is set. Okay? And of course, it now has a very fundamental consequences. For example, mechanics or kinematics, like the simplest part of mechanics, start from the most fundamental object, which is called particle. What is particle in kinematics? How you characterize the particle?
An object with mass but doesn't have
Kinematics. Mass is about dynamics, forces.
Position and momentum.
Position and momentum. That's what means particle. Particle means position and momentum. And then, of course, what we know, and again, I'm not. So if I'll take now x, which is p minus the p expectation value, and my z would be coordinate minus its expectation value, and we know that in x representation the px momentum is h bar ddx, h bar, then you can compute px commutator, and it's equal to h bar. Okay. So now you say that this product of variances, you can write sigma variance of a momentum times sigma variance of a coordinate, and if you take a square root out of it, and this is bounded by h bar over 2 times d, where d is dimensionality because different components do not commute. So this is a bound of it. Now, of course, variances depends on the state psi. I could be in this state, my particle can be free particle moving somewhere, or my particle can be a particle in some field, or my particle can be in a crystal. There will be very different psi's for this case. So you may ask, because it's inequality, what psi saturates this inequality? What type of a psi in a momentum or in coordinate representation? For example, in a coordinate representation, just some function of coordinates. It's a complex function of coordinates, you say, for which psi you can have this inequality reaching its limit, namely the lowest product of uncertainty. And I don't do it now. It's a very nice and interesting exercise. This could be on the exam, so we'll solve the respective problem. It's at the end of this section, and the solution is in the end. The answer is Gaussian. Whatever sigma x, sigma cube. Okay, and then because the momentum is this thing, then the eigen mode of this would be Fourier transform of this, and Fourier transform of Gaussian is also Gaussian. And for this, you can say that this is really bounded. So this now statement would be independent for Gaussian packets. You can say that sigma p, sigma x is equal to this. It's just a statement. And generally it's bounded by this. But on the other hand, we know that the entropy of a Gaussian distribution, how it's related to its variance.
It's the maximal Fourier variance.
We, the previous lecture, used it 20 times. So what is in rate distortion theory? We were dealing with Gaussian distribution. We were computing mutual information, which was the rate of transfer through the channel, minimal to reach to give a given distortion, and we were always using formula for entropy of a Gaussian channel.
F of log of.
It's a logarithm of its variance. Okay? Generally, it's a straightforward thing, and it's something which I think really is useful. That's why any useful statement I will be repeating at least 3 times in 3 different lectures, so that it will sink. So I can also write this, and this took surprisingly long time. Deutsch did it 50 years after Heisenberg, to write this in this most natural language, which is entropic. It tells you S of p plus S. So you take logarithm of this inequality, which was done in 70s. And sometimes it's hard to believe that the most natural language of uncertainty is entropic. And this was formulated in a very, very particular case, because Heisenberg was thinking about free particles, and then of course the variances is enough. For Gaussian distribution, variance is the same as a distribution, right? But generally, you need to talk about entropy. So the general statement is the following: that's larger or equal z d. Okay. Okay. So you have this half, and then you have this half, and they cancel out. Okay. This is the uncertainty relation in this century, right? This was 1926, and this is, and now generally it's true for any distribution, and it's a very non-trivial thing to prove. And again, we aren't proving these things, but this is an entropic language in which you express uncertainty relation. Okay, and now for us it's really a statement about information theory, which means that your sum of your uncertainties are bounded. Okay, and again, maybe I'll do it on tutorial. I really don't want to do much of linear algebra, but I still say a few words. What is the geometric picture behind this D? You can say, what does it mean that 2 matrices do not commute, X and Z? If you still remember your linear algebra, it's the following statement: that you can take a matrix. This matrix, you can find for it its eigenvectors. In the space of this eigenvectors, this matrix could be diagonalized. Namely, if you take these eigenvectors as your basis, and you also happen that they are orthogonal, and you can always normalize them, then you can write your matrix as a diagonal matrix on which what will be staying on the diagonal is just eigenvalues. Okay? It is in this basis which diagonalizes, let's say, X. And now, if you write it in this way, then you will find this X matrix as something which would be diagonal, and here it will be X1, XD values which are here on the diagonal. Now, and of course there will be probabilities. They would define probabilities of different values of X for a given state. Now, you can do the same for Z. Z, and there are another, so there is this, and we can denote it like this. So those are eigenvectors of this matrix, and those are eigenvectors of this matrix. The statement of non-commutativity means that they are different. You cannot diagonalize both matrices in the same basis. Because if you could, then would definitely diagonal matrices commute. So the statement is that it essentially tells you that this set of vectors is different always. That's like d-dimensional. And so what actually stands here in a most general statement, which just for a change, in the book I give a proof of it, because I really think that it's kind of, well, it's relatively short and it's important. So you can prove that what stands here is x z squared. So this is an overlap or projection. Right? The fact that x and z are different, it means that you take any x and you try to project it on a different states of z. And it's generally non-orthogonal to all of them, right? That's a non-zero projection. And this projection is something which determines this thing, because it's related to non-commutativity. And this bound means that this is something bounded by 1 over d. When this projection is 1 over d, it's called unbiased. Namely, you take any vector and you ask, I have d vectors of orthogonal basis. What would be my average projection on which of them? Well, 1 over d, if it's unbiased, right? So if you rotate over all possible. So what I'm saying is that this form of writing it, it's related to the simple idea that non-commutativity of matrices means non-orthogonality of their respective sets of eigenvectors, and what stands here is just what is called the most unbiased projection. Okay, question?
Can you repeat? Those are all the x's projected on all the z's?
No, it's a value. Yeah. What is stand here? Well, essentially, in a statement, what stands here is a maximum of x, z, right? Squared. Which is essentially tells you that you take arbitrary eigenvector of x, project it on different z, look at the maximum of it, right? Or you take z and project it on it, will essentially the same. It's a degree of their non-orthogonality. And sometimes they are almost orthogonal, namely that this commutator is very small. It happens, right? Again, h bar is very small, right? Depending on which units you are working. But it just translates this statement, which is a little bit algebraic, statement which is somewhat more geometric. And I think that it helps me when I can, have a drawing instead of formulas. Okay, so now we added quantum mechanics questions. Yeah, it's one while I was studying, you get all quantum mechanics. Okay, good. No questions. Then, of course, to move into information theory, I need an object which people use because it's an analog of a bit in the classical information theory, and it's called qubit. So let me introduce this notion of a qubit, and then we go for a break, and then we get into quantum statistics. Yeah. So, bit is a notion of, it's an amount of information which corresponds to the choice between two possibilities, but then again with the typical abuse of terminology, which all natural scientists, and I hope you too will be doing all your life, is that we can call bit also a physical system which can have two values. For example, spin up or spin down, or neuron which fires or do not fire. We can call it kind of a classical bit system, so we can now define a counterpart to it, which we'll call qubit, and Q will be from quantum. Qubit. So it's like a quantum coin. The classical, of course, long before Ising model neurons and spins, there was a coin. So the physical idea of a bit was, of course, a coin which can go this way or can go this way. So now this is a kind of a quantum coin. We say that it could have two states, 0 state and 1 state. and which means that generally any state of a qubit is a superposition where A and B are complex numbers, and sum of their square is unity. So now, if we do this thing with what is the expectation value of any operator, because of this superposition, we can write it that this is the A squared 0, O, 0 plus B, well, A modulo squared plus B. Do I need to write it as I do integral product? So here I would put A complex conjugated 0 plus B complex conjugated 1. And here I would put A 0 plus B 1.
Would be rough.
Huh?
Would be.
Yeah. Well, I need to do it like this. Absolutely right. It's ket. This is bra and this is ket, right? That's when your father tortures you at every dinner so that you won't ever say an extra word. That's what Dirac's father did to him. Then you start to be very, very precise and compact in your terminology. So what do you find out? That, well, this times this would give you A modulo squared, this would give you the B modulo squared, 1 O 1, and then you would have something which is what we call interference, right? So you would get A, B complex conjugated plus B, A complex conjugated times 0, O, 1, right? It could be that operator O is not an operator for which 1 is an eigenvector. So which means that O matrix acting on 1 would give you non-zero projection on 0, right? And then it generally is something that you can measure, and it tells you that the superposition is not only sensitive to these numbers, their magnitudes, but it's sensitive to their phases, right? It could be that this is 0, right? Well, depending on what is the imaginary part of this with this, right? Okay, and okay, now again, what we learn from basics, we say that, look, I mean, who is interested in it? So if this qubit could exist in any superposition between 0 and 1, so it's like a coin, which is not this, but kind of could stand at the arbitrary angle infinitely long until we measure it, and then it collapses on this side. But generally, what we now understand is that even though we cannot directly measure the quantum state, this quantum state potentially contains an infinite amount of information. Because, of course, you impose a condition that A squared plus B squared is equal to unity. So on two complex numbers, you impose one condition, it boils it down to three-dimensional space, and you can say if overall phase is unimportant, it brings it down to two-dimensional space, which is essentially a complex vector, but it's huge, right? It's infinite amount of bits. We discussed in rate distortion theory that even to encode a real number, you need an infinite number of bits with infinite precision. So in principle, the evolution in the quantum world exists in this unbelievably great space. We somehow can measure some projection of it, but this is something which is now really people are really trying to explore in different ways. Okay? Any question about it? This is quantum mechanics, and this is a quantum object. Okay? Question?
You use the fact that O is symmetric?
O is always a matrix. Any observable is a matrix. Okay?
We assume that if we take 1 and 0, 0 and 1, it's the same.
Yeah, it's the same. Because it's now a real number, so it's invariant with respect to complex conjugation. changing this and just making complex conjugation. Right? So instead of this, here you would make A, and here you would do A. Be my guess. It's the same answer. Okay? It's called internal product. Okay. So now, in this very fast way, we go from 1925 to 1927, just 2 years down the road, when people, namely Landau and von Neumann, who read Landau, immediately recognized the very dramatic consequences of this Heisenberg statement for a fact when you start to consider composite system. And the idea of entanglement appears. Okay? So now, let's consider a state of two systems. Again, it's always will be A and B. And of course, now quantum people call it Alice and Bob. But essentially, it's not that important. So we just have two systems, two physical systems, which potentially could interact, or it could be non-interaction. Or they can go somewhere, and then we can bring them to interaction. And of course, it's together, that's a quantum system. We can characterize it by a vector, but this vector now lives in the space of dimension, which is a sum of their dimensions.
Product.
Product of the dimension. So if A lives in some D1 dimensional space and B in D2 dimensional space, then the AB, for every state of A, we can have every state of B. Okay? And generally, you can have ask what could be psi AB, and one of the simplest cases, can you just take whatever is psi of A and make a tensorial product of psi of B. So let me just explain what is a tensorial product. Let's say if I just take a simple two-dimensional vector AB and take a three-dimensional for simplicity, three-dimensional vector CDE. So this is B lives in a three-dimensional space, and these are coordinates in this space. This live in two-dimensional space. Tensorial product is, as we discussed, must be a vector in a six-dimensional space. And tensorial product of these two vectors is just AC, AD, AE, BC, BD, BE. Okay? That's clear. So now we can say, well, this state CAB could be a tensorial product. This is simple case. Namely, it essentially tells you that they are independent. In a moment we'll see it. Like for every A, you can have every B, like taken like this. So for example, if I compute any observable, and I would make it only observing in A. Whatever it does, when acting on this guy, it does not act on this part. Namely, this is some 2 by 2 matrix in this case, right? It's 2 by 2 matrix, it does not do anything to your other 4 dimensions in your 6-dimensional space. Only acts on this. But these two are, these A's and P's, they are presented everywhere, right? So let's see how it works. So what I would say is that I would make it in B just an identity. If I put identity here, it would just give me unity. Yeah, because it's a sum of and I would now take it and multiply it by by act on CAB here and CAB here. So now, of course, B will be acting on this, and A will be acting on Z. So what I would essentially obtain, I would obtain that Z would be psi OA psi and times psi B IB psi B, and this is unity. So it's the same as if I just make my measurement on A. And this is the statement. In this simple case, when my quantum state of a composite system is a tensorial product, then any measurement on A does not know on B. Okay? You observe B, you not observe B, totally irrelevant. Okay? Now, if you generally can say that there could be a sum of such products, that's non-factorizable. Okay? So now the question which I asked before we go into break is that because any state of a quantum system is generally a superposition, so when I consider factorizable, namely I take arbitrary superpositions of A times tensorially arbitrary superposition of B. Or I can take arbitrary superposition of AB. Okay, that's an arbitrary superposition of all possible state of 2-qubit system. So now as we go for a break, so you'll think and meditate whether it could be always presented or it couldn't be presented as a tensorial product of superposition of A, any, times any superposition of B. Okay? That's the question. 15 minutes. Okay, so I hope that you've realized already, but let me still write it down. So this is a general superposition of a 2-qubit state. If I now take a general superposition of A, which is alpha 0 plus beta 1, and I take a general superposition of B, which is alpha prime 0 plus beta prime 1, okay? And if I now take a tensorial, okay, so what is 16 minutes. So what now I'm saying? I now want to show you that tensorial product is a very particular degenerate case of a composite state. So a general state of a 2-qubit system is a superposition of 4 possible states of a 2-qubit system. Okay? Now, if I take arbitrary superposition of a 1 qubit and arbitrary superposition of another qubit, and I make a product, psi A tensorial product with psi B, right? So what I will get alpha prime 0 0 plus beta. What's all this dice gonna be? Plus beta prime 1 1 plus alpha beta prime 0 1 plus alpha prime beta 1 0, right? Why this is not this?
We have some connections here between the
Yeah. If this is my A and this is my D, then A times D is the same as B times C, which is not true here. Right? This is just 4 arbitrary numbers. The only condition is that they are. Of course, you need to check that some of this squared is unity, some of this squared is unity. You can also count how many degrees of freedom you have, how many conditions. But this is a simple thing to say that just for the very fact that what you have is a superposition. I won't use anything here, but just a statement that the arbitrary state of a quantum system is a superposition. Arbitrary state of a composite system is a superposition, and it's not generally a tensorial product of 2 superpositions. Okay, That's totally fundamental statement, which means, and that what Landau immediately, he was a PhD student at the time, of the age 19. 19, yeah, and he immediately recognized that if this superposition stuff is true, then now what stands here is a sum, right? So generally you cannot present it as a single tensorial product, right? Well, generally, of course, you can say, wait, but if now, I mean, my psi A is some kind of, how I denote it, yeah. Somebody remembers what a Schmidt decomposition is? Or singular value decomposition? So let me give you a short, because generally now one can say, well, look, this is terrible. If my psi A is a superposition and psi B is a superposition, why is a single sum here? Maybe it must be double sum. One sum of a superposition on A and another sum of a superposition of B, right? Because generally it's yeah, where is my, yep. So if you say that why it's not psi AB is alpha ij, psi ai, psi bj. Why it's not a double sum and a single sum? Okay, like this. And for this, there is a beautiful mathematical theorem which called singular value decomposition or Schmidt decomposition. There are different ways. It tells you that you can always make a rotation in the space. Namely, you can introduce your psi A. Well, let me call it phi and phi because now I introduce. Well, essentially it tells you that present this alpha in the following form, this matrix alpha, as uik dkk vkj. Phi, let me write it, a phi bj. So, of course, generally, what Schmidt tells us that you present as a double sum because there is a superposition here, there's a superposition here. But you can always introduce for any matrix here, and this is a matrix which has it's a stochastic matrix, as we discussed, as a unitary matrix, diagonal matrix, you see there is kk here, and another unitary matrix, and this you can call this quantity nu psi k, which is uik phi I, and then you can use this quantity as in u psi b k, and that would be it means that you just resum your vectors into new combination with this coefficient. So for any such a double sum, you can present it as a single sum over k, psi I k, psi a b k. Okay, so at least there is a relief. There is a single sum, but it's a sum, and this is an analog of in the quantum world of what we had a statistical dependence in the classical world. It means that it's definitely that whatever value of A you choose, then for value of B depends on it. So there are some, here it's the coefficients, here it's Pi's and Pk's, and then of course you can show that they are positive because they would determine the probabilities. And you can normalize so that there are some sums into unity. This is just how you choose your vectors of the state. So this is the most fundamental statement, was that you generally present a state of a composite system as a sum. It could be only one term in this sum. Then you call these systems A and B unentangled. The moment there is two or more terms in this sum, you call this A and B entangled as a definition. Okay. Now, if you do this game over here, and your psi's are now these guys, so what you would get, you would get here the following things. So you would have a sum over I and j, and that would be square root of pi pj, and there will be psi a j o a psi a j, and psi a I j. So you take, when you do it here, this would be a sum, and this would be over here a sum, right? So you have a double sum, j, and this would be I. Okay, and now you plug it here. So B will be acting over here on CB of CB of J, CB of I. Okay, and sorry, this is square root. So this is the square root of positive number. It's a coefficient. It's squared would determine the probability. So that's why I call it p square root of p. So that when I square it, it will be like in classical probability. So it's just my notation, so that I would use this coefficient as a square root. So they come here as a square root. This is now my O I J I J. This is from the left. This is from the right. This is coefficient at the left, this is coefficient at the right. You follow me? You want me to write it in more details? Huh? This means that no, not writing or not following. Okay, good. So now what this give me? This is identity operator. It gives me delta ij. Okay, which tells me that now the result of this measurement of psi a b o a I b psi a b, when my psi I b is this one, would be equal to sum over I pi, because I is equal to j because of this delta function, psi a I o a psi a I, which now it's different from what we had before, where we just have kind of no B. We now have the states, and we have a sum over all the states. Or, as for Neumann notice, you can write this formula as if you trace a matrix. It's a sum of different elements. Each one is positive, and the sum of pi's is unity, as we discussed. So you can say that this is a trace of some matrix rho A times your matrix OA. So there is a product of two matrices. One matrix is my observable, another is matrix which is defined, and it's called density matrix. And it's a sum over I. And so you take, it's a matrix, right? So you kind of symbolically write it let's say, I and with pi's here. Okay, so generally in this matrix there are could be no diagonal elements. You can always diagonalize it. It's diagonalizable, and any measurement is a trace of your observable with a product with this matrix. Let's do it with a qubit for a particular case, so that will all will be less abstract. So let's take a non-product entangled states. Well, simple. So let's take psi AB as A 0, 0 plus B 1, 1. Okay. How I defined a matrix. So this is a vector, right? It's a vector in the this four-dimensional space, right? There's 2 dimensions 0, 1 for A, 2 dimensions 0, 1 for B. So this is a vector. Okay. Now what Landau tells us is a very strange thing. You see, in classics you define the system with a vector of probabilities. In quantum mechanics you define the system by a complex vector state. It's still a vector. You wanna describe A. What you need to do to describe A is to introduce a complex matrix. Okay, let's see what it means. So it says that let's define rho A as a trace over B. Trace means that you take sum of diagonal components. That's the definition of what to take a trace of matrix. So you'll have this matrix now. Let's define it. So how you would do it? You would take this and make it tensorial product on its. So you would do an A. But I'm not doing tensorial product. I'm doing inner product. Sorry, this is wrong. Okay. So what you would do? You would do the following things. You would take 0, 0, 0, 0, right? So it is in this matrix, it is this element over here. And the coefficient will be A squared, right? Now you would take 1, 1, yeah, 1, 1, always here. 1, 1, 1, 1, namely over here, and this would be B squared. But there will be also these things, right? Which would be A B 0, 0, 1, 1. You notice there's no 0, 1, no 1, 1, 0. We won't do all the, quantum communication theory. This is the most entangled state, right? Every time this is 0, this is 0, 2, and when time this is 1, this is 1, 2. It's called Bell state. I mean, I've chosen it not kind of arbitrarily. But you see, but at least there is not a huge kind of variety here. So I have this, and I will also have A, B complex conjugated 1, 1, 0, 0. And of all this guy, I now take a trace on B, namely on second sinks. Only when my second sinks coincide, right, I sum it. When they don't, I just don't. Okay? So what I get as a result, I will get a matrix which would be having, and again, the coordinate here 0, 1, 0, 1, so that will be A squared, B squared. This is my rho A. Okay? And by the same token, if I now, by this formula, would compute any OA, so I take, let me just continue this, where I, if I would now, So what in this formula now, if I do this, I can write it as a trace with this, or I can directly substitute psi complex conjugated. This thing complex conjugated over here, this other thing, and then what will I compare? I will obtain the answer, which is a squared 0 O A 0 plus b squared 1 O A 1. Did I already? Yeah. Okay. So now I want to return to the very beginning of the first lecture and remind you that this is the expectation value of your operator O in the qubit, which is in a superposition. And this is an expectation value of a qubit which is a part of a composite system. All what I did, you can forget what I did. This is the answer, right? You can check it in many ways. Okay? So, and this shows you the difference between being described by a vector. This is my psi A, no B whatsoever. Psi A is a superposition A0 plus B1. Okay? This is two qubit system A00 plus B11. Okay? Now I'm saying, in this case, I'm observing only A. That means that I need to, what they call, trace over B, right? I need to sum over all possible values of B. What I get as a result, what is the difference between this and this? The main staggering difference between this and this.
No, there are no interference.
No interferences. No this term which are sensitive to the phases. Right? I am in a quantum state. A and B in a quantum state, or they like to say a pure state. Right? The fact that you observe only A generally means that you are now not observing any phases. Moreover, you need to characterize yourself by a matrix and generally not a vector. It's terminologically it's called mixed state, and this is pure state. Mixed state, that means that you are with this probability in zero state, with this probability in one state. Here you have both states until you measure. Okay? But when you repeat your measurement, that's the expectation of different answers. Okay? This is a very, very difference. This is quantum mechanics and this is quantum statistics. And then it introduces you a new mathematical object. Okay? Think about it. Any questions? They're all related to each other. What is uncertainty, Heisenberg uncertainty, for example, for coordinate and momentum means? It means you cannot localize physical system. You want to describe any mechanical system, it's described by coordinate and momentum. Or it's positioned in a phase space. Here's coordinate, here's momentum. Here is what is my system? It is this. You have gas in a box, it's a 6n-dimensional space, but nowhere. Every state of a system is the coordinates and position of all particles, it's important. Now you cannot. It's a box. Okay? And the fact that you cannot localize any physical system essentially means that you also cannot divide any system into two. That's the meaning of entanglement. Of course, it's all follow from kind of different properties, but of the same linear algebra. Just the fact that you assume that you are working with linear algebra, that's what you get. Okay? Questions? You find it, you don't find it bizarre or anything, or you just get used to it.
Like both are probabilistic in the sense that like you cannot predict the measurement outcome, right?
Yes.
But you're saying that the pure state is a deterministic state. Like you cannot predict the measurement outcome, but
The measurement outcomes you predict with a certain probability, but this probability depends on the phases between A and B. You see, you did a mixture over here, right? You did a mixture, and in this mixture, this is determined by complex number. Relative phases between this complex number essentially would mean, imagine that it starts evolving in time, it starts evolving by exponent I energy time t. So phase is important. It's like where you start in your evolution. You spin rotating, you rotate from here, you rotate from here. So you rotate differently. All this information wiped out here. Okay? So in this sense, they correspond to probabilistic description, but different. One is a probabilistic description in which you start from a dynamical evolution. This vector, the vector of superposition, is something which evolves mechanically by a law of quantum mechanics, by Schrödinger equation. This is already statistical description. Okay? There is no kind of, there is an evolution of it, but it's an evolution already of a probability distribution. Here you are either in this or in this. Here you both in both states. Only when you measure, you collapse. Okay? Maybe it's a good time to write less formulas and discuss what is actually the measure. Yes?
So what is the difference in the target state? How is it different from a probability distribution that changes in time? Just a normal...
Well, everything changes as time. Density matrix, this rho A, it also changes as time, governed by the same Hamiltonian. So the point, it in principle contains different information. It contains less information. Okay? In a moment, I'll write, okay, let me write von Neumann entropy, and then I'll do some kind of interpretation. So generally, as long as you see that you, by tracing out B, which is jargon I don't actually like, but if you just think terms not observing B, okay? So if you're not observing B and only do your measurement in the subspace of A, this is a statement. You describe expectation value of your measurement, not by a vector and taking internal products of these vectors as we did for states, but taking a matrix and taking a trace of this matrix. That's a formal statement. Okay? Now what von Neumann did in like 2 months after Landau, and I'm trying to realize if von Neumann was also a PhD student. No, he was a master student. He already got his PhD in mathematics, and he was a master student in chemical engineering, which he promised his father to get a diploma, because all the rest was not a real profession. So what von Neumann did is that he defined related entropy. He said, if I now have this matrix, rho, then I can identify with it the entropy, which would be a measure of trace rho log rho. Now we used to take trace of we used to take this with the numbers, right? Now, of course, rho is also a matrix. It could be multidimensional. What it tells you is that when you take here this matrix rho, the trace would be a sum of elements. But there is this logarithm, which is, of course, this mathematically not that very trivial, but on the other hand, this density matrix is always diagonalizable. You can always find already in your new state in which it would be diagonal, and there will be just p's standing on it, and that would be, in this case, will be usual Shannon-Gibbs entropy in this case. And generally, of course, you can still work with a logarithm of a matrix as if it is a matrix. It's just a well-defined in mathematics object. Okay? So what von Neumann says is that you take this, and this is a measure of uncertainty. Which uncertainty? It looks like Gibbs, but it's not. But it's very similar. And what is Gibbs entropy? For example, if you are Gibbs, namely in the state of 1878, you think about physical system. You say, look, I observe a system macroscopically, and this entropy is, if you look just at Boltzmann formula in a very simple way, Boltzmann is a logarithm of number of states. Which states? Microscopic state of this molecule which are compatible with my macroscopic observation. So in this sense, you can say that the Boltzmann-Gibbs entropy is a logarithm of a number of microscopic states which we do not observe, but they are compatible with what we observe. What is von Neumann entropy? It's a logarithm of some number of states. Of what?
Quantum states of A.
Logarithm, entropy must be logarithm of something unobservable, possible, not observable. It's a logarithm of a possible number of states of B and the rest of the universe, for that matter, which are like particular. Well, in the textbook of quantum information, say, and the rest of the universe included in this pure state, which is compatible with any observation on A. That's essentially meaning of von Neumann entropy. So you say that there's something which is, you characterize now A not by a vector but by a matrix. Matrix means that you somehow characterize state I and state J. What is the element rho I J? There is a possible state of system A which is psi I, and there is another state psi J. What is this element in the density matrix characterizes? It characterizes possible correlations between the states through B, which we do not observe. And what von Neumann say that this, when you obtain this density matrix, and you obtain it in this, for example, very particular simple way, just take a trace of two-qubit system, it tells you essentially logarithm of possible states of B compatible with your measurements on A. Okay, that's its meaning. Okay, I probably want to do now more computations. Maybe I'll say a few things about interpretation. But then again, as I always say, that the moment you don't calculate that it's always get personal. What happens when we do measurements? What actually happens?
You are telling your system is the measurement with the environment. So.
Yeah, I take my system, which, as we say, was in some kind of state, quantum state, and as we say, collapse it into a single measurable value. It, in principle, was in a state. If I prepare the same state and measure it again, it would give me different value. Possible. Okay. When it happens, what it means collapse? Because this collapse of wave function, people discuss for the last 100 years, more or less non-stop. So you say that I have my quantum system and I attach a measuring device to it. Okay, good. It's still a quantum system, right? There is nothing about any system is quantum system, right? And people say, well, microscopic, macroscopic. Now, after all these Nobel Prizes about cold atoms and helium, we can have a macroscopic system with a Avogadro number of atoms. If they're cold enough, it's quantum system. It's quantum. So what actually happens when we attach a measuring device? It's not quantum system. Where does this collapse happen? And then Einstein said, in his Einstein-Podolsky-Rosen paradox is even more dramatic thing. He said, what you're telling me is that when you do measurement, you immediately collapse this quantum state and it has a definite value. Imagine that you have a particle with a spin 0 and it decays into two particles, and then we know that these two particles has one spin is opposite to another because they came out just by conservation of angular momentum. Okay? So now they are now flying to the different ends of the universe, and then you measure one of them and you find its spin. You immediately know that the other guy over there has an opposite spin. That's Podolsky was in technical. Yeah, somebody may agree. So how are we to understand this? And I think that this is, there are two ways of, well, then there are three ways. The first is shut up and calculate, which is a very decent attitude. And then what I've noticed, because I live long enough, that the same people who are advocating this when they were like 30 or 40, like getting their tenures, and they want to shut up and calculate. When they get to 60s and 70s, they started to do interpretation. So as now I'm getting, it's my birthday today. So I'm 16. So I want to give you, I mean, the same David Mermin who said shut up and calculate, even though the same Feynman, he suggested his interpretation, and Wigner suggested his interpretation. But technically, what people are doing two different things. First of all, it's called quantum decoherence, and it's a very, very technical discipline. It's a look. I had this quantum superposition. Let's say there was this kind of my coordinate was one possible value. This is just two possible values. So I had some kind of quantum superposition. So there was like, but maybe not even without, maybe even without maxima. And then, of course, this is only one space, but there are other multi-dimensional space of coordinate, and somewhere I attach to it a measuring device, and they start interacting with the measuring device. It's still quantum evolution. Quantum evolution has the same Liouville theorem, which is in the classical dynamics. It preserves entropy, it doesn't change, it does not grow. It's a dynamical process. But it starts, kind of probability starts leaking into different dimensions, and then they say, as it spreads another dimension, it shrinks in this. So my device is about measuring coordinate. But of course, it's a big device. It's a macroscopic system. It interacts with the environment. The environment has its many degrees of freedom. So probability like leaks in another direction, but what it changes in time, in this respect, that it will be getting into very, very sharp peaks around this value and spreading into us. This is, in a sense, technically, it's the most important thing that people do, not in practical quantum computing and all this, which is very technical discipline, but in fundamental things. Quantum mechanics lives in Hilbert space, right? Every qubit is a complex number. It's an infinite. It's a huge space. It doesn't live in all of it. Somehow, what we don't understand and what people, I mean, best people, I think, in this most now, trying to realize in what parts of this infinite Hilbert space it actually lives. Because a classical space, when we do measurements, it's either spin up or spin down, right? It's like two values. Right? This, not without all this huge, mixture by a complex number. So what people try to really quantize how interacting with a really system which has more and more and more degrees of freedom, it rearranges your probability and getting, then, but then you measure, and it's either this or that. What happens? What is the? It must be kind of qualitative, right? So you cut the tails. What happens? And who cuts? God. As Laplace said to Napoleon, I don't need this hypothesis. There are many ideas. One idea is that quantum mechanics is essentially it's an information theory. which means that quantum mechanics does not describe a real world, whatever you mean by a real world. It describes our expectations. And in this sense, it perfectly makes sense, right? Because it tells you that quantum objects do not exist. There is no quantum particle. Because particle is what?
Wait.
Particle is coordinate and momentum. This is a definition of particle. What is the particle? Right? Well, you can make a bodies, but a particle, point particle, has coordinate and momentum. Such object does not exist in quantum mechanics. Okay? And this is a statement which I like it, so I quote it. Correlations have physical reality. That which they correlate does not. For example, a momentum of a particle with a coordinate in a different direction coexist. Coordinate of different particle coexist. Many things that we compute are actually correlations. Objects which exist, which we talk about because we get used to it, they do not exist. Or they exist in a state of superposition, if you wish. Okay? So one idea is that you cut this process when observer enters this game. An observer observes. An observer is something which is not described by the law of quantum mechanics. Namely, he cannot be in this superposition. It's an assumption. It's just not an assumption. It's an interpretation. If you look from this viewpoint, this Einstein-Podolsky-Rosen paradox disappears immediately, right? Because you say, where the collapse happens? Collapse happens in the head of the observer. So the fact that you here observe this particle, and you know about that particle, it still is the same head. Your head is here. If you want the observer, which is over there, near the other particle, you need to send him a physical signal giving your information which is in your head. Okay, this is still speed of light. There is no contradiction here. Okay, so our problems, as many things in 20th century, we realize that, like, you know, who shaves the guy who does not tell you, like everyone, like all this Bertrand Russell, etc. There are things that you can formulate many things. Or like Gödel said, you can write many statements with an arithmetic. You just cannot prove any statement. There are some statements which aren't proved. There are some things which you can ask, interpret it as a part of a real world, and it's not part of a real world. You need to interpret quantum mechanics in this sense as a set of our expectations about measurements. And in this case, it has perfect sense. Absolutely. I don't see any paradoxes in this way. Just the same way as in 19th century people tortured Boltzmann and told him that about this entropy growth, etc. And it's all, in the moment you start understanding entropy as your measure of uncertainty, and then you start understanding that as time goes on, that generally if you had any uncertainty, it can only grow because you can worse and worse predict the future, and then it is because you have now worse predicting up to this moment, that even worse predicting up to this moment. If there is any ignorance, it fills the space. So there's no contradiction here, it's rather common sense. So I think about quantum mechanics, to a large extent, it's still technically very interesting to see where this probability is. It's a really very non-trivial and very technical part of modern physics. But conceptually, the moment you start treating it from the information viewpoint, okay, so this is our expectation. And it's natural that our expectations are multiple. In principle, they can have multiple values. And quantum mechanics suggests you a very convenient and simple formalism to handle this expectation. The moment you want to interpret it and start asking questions, well, this particle did not, this Pauli particularly like laughing at people, asking questions which he himself asked like 5 years before that. What I mean, like this qubit, this spin, it did not exist before I measure it. This is an idiotic question. Your quantum mechanics is something which predicts results of measurements out of it. Okay, this is my personal interpretation. There could be probably other interpretations. Questions? unexpected twist in information theory. Okay, so tomorrow tutorial will be about money and bacteria, and next week we'll return back to quantum and black holes. Ultimate, ultimate information box. Yeah.
I have two things. One is a bit technical and one is a bit non-technical. I'm not used to think about this from an information point of view. It's really interesting. If you have